Vegapod Hyperloop is a student team based at MIT World Peace University in Pune, dedicated to the advancement and scalability of Hyperloop technology. Our focus revolves around implementing Hyperloop technologies such as contactless propulsion, levitation, and vacuum on a scaled-down model. Our team has participated in events like the SpaceX Hyperloop Pod Competition, European Hyperloop Week, and the Canadian Hyperloop Conference, representing India. Established in 2019, Vegapod Hyperloop asserts several achievements to its name. Our team comprises students from various engineering disciplines, including mechanical, computer science, electronics, electrical, and civil, as well as students from media and management courses. The team structure includes 3 divisions: technical, business, and research. The technical team is responsible for practical aspects of building the pod and the necessary infrastructure. The business team encompasses departments such as sponsorships/partnerships, logistics, finance, operations, and media marketing. The research team works on comprehensive technical and socio-economic reports related to full-scale Hyperloop implementation. To start with, let's take a quick dive into the innovative design of our last year's Hyperloop prototype. Our 90 kg subscale model featured a cutting-edge monocoque metal composite chassis with an outer shell crafted from flax fibers for minimal aerodynamic drag. The heart of its speed, a linear induction motor, mounted on the chassis bottom, empowered the pod to reach a top speed of 70 km per hour, generating a thrust of 292 Newton. This pod wasn't just about speed. It also boasted an advanced contactless and fail-safe lateral stability system. Safety was paramount, with friction and eddy current brakes designed to haul the pod within just 15 meters. In the realm of data and health monitoring, each subsystem was equipped with its own vehicle control unit, feeding data into the master VCU. This system enabled real-time health assessments across the pod's systems. Powering all of this were 3 distinct battery systems: a 14.8 volt low voltage system for sensors and computing, a 37 volt medium voltage pack for stability, and a 177.6 volt high voltage system dedicated to propulsion. Our trajectory design was meticulously planned for a 100-meter track. This pod would ramp up to its maximum velocity in just 58.8 meters, thanks to the calculated thrust. Upon hitting this mark, the motor would power down, activating the braking system and bringing the pod to a smooth stop by 74.34 meters, with a significant buffer zone for safety. All this power and precision and energy required for just a single run, just 8.1 kilowatts. This blend of speed, safety, and efficiency encapsulates the essence of our Hyperloop prototype's design.
The chassis of the Hyperloop pod is like the skeleton of the vehicle. It's made from a strong combination of metals, mainly aluminum, and we built it in a way that it forms one solid piece. This design makes it really good at handling different kinds of forces, whether they come from inside or outside, ensuring the pod remains sturdy and safe. Despite being strong, it's also quite light, which is important for speed and efficiency. The chassis is cleverly designed to fit all the necessary parts and systems of the pod neatly and securely, making it the core structure that holds everything together. I'm thrilled to share insights into the design of our Hyperloop pod's chassis, a marvel of engineering balancing robustness, sustainability, and innovation. We choose aluminum alloy 6061 for its lightweight yet strong nature, crucial in a structure that needs to endure high operational forces while remaining sustainable and cost-effective. Our approach involved topology optimization, a method that identifies where material can be removed without compromising strength, focusing on stress zones and force flow. This allowed us to create a chassis that's not only sturdy and durable but also weighs just 8.7 kg and measures 1.25 meters in length. It's a testament to efficient design, optimizing space and material use. The dimensions from the 440mm width to the 105mm height were meticulously calculated to accommodate key components like the linear induction motor and braking systems, ensuring optimal space utilization and performance. Special attention was given to the fillet design, with radii chosen to minimize stress concentrations crucial for the chassis integration. Under load, the strategic placement of cutouts guided by topology optimization ensures weight is saved without sacrificing safety. The chassis is a cornerstone of our Hyperloop Pod, embodying our commitment to innovation, efficiency, and the future of high-speed transportation. In our pursuit to refine the Hyperloop Pod design, we embarked on an extensive analysis and simulation journey. Initially, we crafted a detailed surface model of the chassis in SolidWorks, which was then transferred to ANSYS for advanced modeling and analysis. Using ANSYS ACP Pre, we developed the layup process, followed by an array of simulations in ANSYS Mechanical. These simulations included static structural analysis to assess chassis stress and deformation under varied loads like acceleration and braking. We examined propulsion forces during movement, braking forces during deceleration, and even a hypothetical scenario combining both. Additionally, modal analysis helped us understand the chassis' dynamic response to different vibration frequencies, revealing its natural frequency. We also calculated the factor of safety using the inverse reverse factor method, ensuring structural integrity under various conditions. To further validate our design, we plan to conduct rigorous physical tests on an exact chassis sample. These tests include tensile testing, 3-point bend test, shear test, compression test, and fatigue test. These tests will provide crucial data on the chassis strength, flexibility, and durability under various stress conditions. The aeroshell of the Hyperloop Pod is like a protective outer shell that wraps around the pod. Its main job is to cut through the air smoothly and keep the pod safe at high speeds.
Imagine you have a futuristic pod, like a high-speed train capsule that moves along a special kind of track, known as an IV. The main goal is to make sure the pod travels smoothly and steadily, without shaking or veering off course. To achieve this, the pod has a special stability system divided into two parts, one for the front and one for the sides. The front stability system. This part focuses on keeping the pod steady as it moves over the top of the track. The track might have some bumps or uneven spots, and the front system's job is to handle these without disturbing the passengers or the main structure of the pod. It's also designed to maintain a specific distance above the track to allow another important part called the linear induction motor to work properly. This motor is key for moving the pod forward. The front system is the only part that physically touches the track, absorbing any jolts or uneven forces so that the ride feels smooth inside the pod. We are proud to unveil a Hyperloop Pod's front stability system, a testament to precision, engineering, and innovation. Our design strategically balances the chassis, countering rotational asymmetry and maintaining a crucial air gap for the linear induction motor. We chose aluminium alloy 6061 for its strength, cost effectiveness, and machinability. Rigorous simulations and static structural analysis, particularly of the bell crank, led to a design optimized for mechanical safety and integrity. Manufacturing involved precision machining using a CNC-controlled vertical milling machine for accuracy and efficiency. Prototype testing with 3D printed components using ABS filament helped validate our design under simulated conditions. This system, with its meticulously crafted wheels and unaltered industrial components, is a cornerstone of our project, ensuring reliability and performance without the need for external infrastructure, setting the stage for our final Hyperloop journey. The Hyperloop Pod's contactless levitation system exemplifies cutting-edge engineering, balancing stability, efficiency, and safety in its design. Central to the system are the magnet mounts and arrangements. After several iterations, the final design employs arch magnets in a hall-back arrangement, chosen for their superior force generation and space utilization. The arrangement consists of 12 magnet hall-back configuration, amplifies magnetic forces on one side while negating them on the other, thus avoiding excess power draw. This setup is critical in achieving the necessary repulsion forces to stabilize the pod, which also minimizes drag and oscillations. For the motor mounts, robust yet lightweight construction was paramount. Aluminium 6061 was selected for its high tensile strength, machinability, and thermal resistance, making it ideal for handling the repulsive and drag forces as well as the weight of the motor and magnets. The motor chosen, a flip ski belt motor, 6374 190 kV, 3250 watt BLDC motor, provides sufficient starting torque to overcome magnetic locking, ensuring smooth operation up to 7000 RPM. N52 magnets, known for their high magnetic forces, were selected for their efficiency and effectiveness in this application. Magnetic shielding posed another significant challenge, requiring a material that could prevent stray magnetic fields from affecting other pod components. After considering various materials, stainless steel 403 was finalized for its high magnetic permeability and strength, forming a cylindrical barrier around the CLS mount to effectively contain the magnetic flux. The manufacturing process involves precision techniques like sheet bending for the CLS mount and lathe machining for the magnetic mount, ensuring accuracy and durability. A unique aspect of the design is the use of a 3D printed PLA for the magnet cushion, providing physical protection for the magnets and the track. The fail-safe system is a testament to the design's emphasis on safety, prepared to counter mechanical or electric failures. This system employs a thin sheet of damping material to mitigate impacts, ensuring the pod stability and integrity in unforeseen scenarios. The assembly of the system is meticulously planned, with the magnet mount secured to the motor shaft, ensuring no axial or radial movements. This precision assembly, coupled with thorough testing, including stability system tests and eddy current evolutions, assuring the system's reliability. In summary, the Hyperloop Pod CLS is a harmonious blend of innovative design, material optimization, and meticulous manufacturing, all centered around ensuring efficient, stable, and safe operation.
Alright, let's talk about levitation, especially how it's used in something like a Hyperloop in simple terms. Imagine you have a train, but instead of running on tracks with wheels like traditional trains, it floats above the track. This floating or levitation is a key concept in the Hyperloop system. Levitation means lifting something up without physical support from below. In the context of Hyperloop, it's like having a magic carpet under the train, but instead of magic, we used advanced technology. There are a few ways to achieve this levitation, but most of them involve magnets. Magnets. You know how magnets have a north and a south pole, and similar poles repel each other? The Hyperloop uses this principle. By placing magnets on the bottom of the pod and on the track and aligning them so they repel each other, the pod is pushed upwards away from the track. This is a bit like trying to push the same poles of two magnets together. They push each other away. Magnetic levitation, also known as maglev. This is the most common method for levitation in systems like the Hyperloop. There are two main types of maglev, electromagnetic and electrodynamic. Electromagnetic levitation uses electromagnets which can be turned on and off to create a magnetic field that lifts and moves the pod. Electrodynamic levitation, on the other hand, uses superconductors and creates a magnetic field when the pod moves at a certain speed. In summary, levitation in the Hyperloop is like having the pod hover above the track using magnetic forces, allowing it to travel very quickly and smoothly without the friction you'd get from wheels on a track.
Braking. Now let's break down the concept related to Hyperloop braking system into simpler terms. Fail-safe braking system. Think of this as an emergency handbrake in a car. It's a backup system designed to make sure the pod can stop safely even if something else goes wrong. The system uses friction like when we rub our hands together and then stop moving due to resistance. This causes fail-safe because it's designed to be reliable in case of emergencies. The system adds an extra layer of safety just like wearing both a seat belt and a helmet in risk situations. The fail-safe system adds another level of safety. It has special sensors and computer programs that constantly check if everything in the pod is working correctly. If something goes wrong, the system kicks into the stop of the pod, the part of the team of safety features all designed to work together. It's like having multiple safety nets instead of just one. Eddy current braking system. This is a more high-tech and efficient way to slow down the pod without actually touching the track. It uses magnetic field to create resistance. Because there is no physical contact, there is no wear and tear on the parts. It's like slowing down a spinning metal disc with a metal held close to it but not touching it. Precision and control. This system can very accurately control how quickly the pod slows down. It's like having a dimmer switch for your light, giving you an ability to adjust the brightness precisely. Since there is no contact, it's quite precise. The pod slows down smoothly like a feather floating down than a ball bouncing to stop. In summary, the Hyperloop uses two types of braking system for safety and efficiency. The braking system is the emergency brake kicking in if there problem. The eddy current brake system is like using magnetic force to gently and quietly stop the pod without anything physical touch to the track. Together, they ensure that the Hyperloop can stop safely and smoothly in various situations. Propulsion. Propulsion is all about creating movement. In case of our pod is about finding a way to make it move forward efficiently and effectively. This is how a boat uses a propeller to push through water, or how a car engines power the wheel. For our prototype, we decided to use linear inductor motor for our propulsion method, and then traditional motor that rotates and needs gear to convert this motion into a straight line. A LIM directly creates linear motion. It is really used for a pod, which needs to move smoothly along a track.
Custom track. The pod needs a path, a custom track designed for sustainability and sturdiness. Our track supports levitation, propulsion, and stability. It's not just a rail, it's a carefully crafted pathway that facilitates the seamless movement of the Hyperloop pod. Cooling. In a Hyperloop, the pod travels through a tube that's almost a vacuum, meaning there's very little air. While this reduces air resistance and allows the pod to travel faster, it also makes getting rid of excess heat a big challenge. Normally, air helps carry away the heat, but in a vacuum, this natural cooling method isn't available. The liquid cooling system works by circulating a coolant to the parts of the pod that generate the most heat, such as the motors and electric components. The cooling absorbs the heat from these components, similar to how blood absorbs body heat and carries it to the skin where it's cooled. The cooled fluid is then recirculated back into the system to absorb more heat, creating a continuous cycle of heat absorption and dissipation. In addition to the liquid cooling system, we employ phase change materials which act like heat batteries. These materials can absorb a significant amount of heat without a large increase in temperature. They do this by changing their state when absorbing heat, effectively storing this excess heat. Once the environment cools or the pod is not in operation, these PCMs release the stored heat as they revert to their original state. This method is particularly sustainable as it manages heat passively without the constant use of energy. By combining these two systems, we ensure that the pod remains at optimal operating temperatures, mitigating the challenges posed by the vacuum environment. This approach not only enhances the efficiency and safety of the Hyperloop, but also aligns with sustainable practices by reducing continuous energy consumption for cooling purposes. In conclusion, the Hyperloop's mechanical design is a striking example of engineering ingenuity and environmental mindfulness. Each component, from the efficient chassis and aeroshell to the frictionless levitation and advanced braking systems, blend seamlessly to create a high-speed travel experience that is both safe and sustainable. The integration of sustainable track infrastructure and innovative cooling techniques further marks Hyperloop as a pioneering force in transportation, setting a new benchmark for speed, efficiency, and ecological responsibility.